Today we're going to combine the last couple of days, solve by factoring, and then sketch our answer to see what it would look like using what we know about end behavior. So these notes are actually the first 4 examples that are on the worksheet for today, the 4.5 Solve and Sketch with Factoring with Notes PDF that is under Thursday's module. So our first example, 2a cubed plus 3a squared minus 8a minus 12 equals 0. So when we have 4 terms and it starts with a cube and it has every term represented, we should think that factor by grouping is probably the way to go. So I'm going to group 2a cubed and 3a squared together. And then remember, when I group that minus 8a, I need to move the negative inside the parentheses. And so then I'll factor that negative out. So for 2a cubed plus 3a squared, the common factor that I can take out of that is the a squared. So I get a squared times 2a plus 3. And then for negative 8a and negative 12, my common factor is negative 4, so I'm going to factor that out. And I get 2a plus 3. So now the 2a plus 3 is my common factor that I'm going to take out, 2a plus 3. And then what's left is the a squared minus 4. Okay, so remember, I'm factoring that out just like factoring out the a squared in the first term. It's not there twice, it's only there once. And then I can factor the a squared minus 4 into a plus 2, a minus 2, and then the one extra step because I'm solving. A is negative 3 halves by taking 2a plus 3 equal to 0 when solving. A is negative 2, and a is positive 2. So a sketch just means I'm going to draw a rough picture of what it looks like. I'm going to be accurate on the x-axis, but I'm not going to worry about how high it goes on the y-axis. So let's see, 1, 2, I have positive 2, negative 2, and negative 3 halves, which is negative 1 1/2. And so now we're going to think about the end behavior. This is an odd exponent, and the leading coefficient is positive. So positive odd looks like a line, a positive line. So it goes up and it ends up, and we'll see what happens in between. So we're going to start low, and we're going to go through that first intercept. We're going to turn around and go through the next intercept, and then we're going to turn around and go through the last intercept. And that's my sketch. It's not perfectly accurate. I know that this number should be negative 12 because that's my y-intercept from up there. And that's enough. The next problem is 12x to the 4th equals 8x squared. So we're going to minus the 8x squared, set it equal to 0. I can factor out a 4x squared, and that gives me 3x squared minus 2. And then set it equal to 0. Now when I do 4x squared equal to 0, I get x equals 0. And this is a double root because it comes from x squared. So technically there's 2 zeros as my answers there. And then I need to solve 3x squared minus 2 equals 0. So we're going to add 2. 3x squared equals 2. We're going to divide by 3. X squared equals 2/3. And we're going to square root. And we have to rationalize this, multiply by square root 3 over square root 3. And I get x equals plus or minus the square root of 6/3, which I'm going to need to get a decimal approximation for. So let's find my calculator. And once I plug square root 6 in divided by 3, I get plus or minus 0.82. So that's going to kind of help me put it on the graph. Remember that my x-axis is going to be accurate, but my y-axis isn't. So I get 0 as one of my roots, and it's a double root. Remember that a double root is going to bounce off of that. And then I have positive 0.82 and I have negative 0.82. And so then let's look at our end behavior. I have an even exponent and a positive leading coefficient. So even positive is up and up. So I'm going to start up top. I'm going to go through my first intercept. And then I'm going to turn around and I'm going to bounce off my double root, which is 0. And I'm going to turn around and go through my other intercept. It should only touch the x-axis 4 times when it's a 4th degree polynomial. Example 3 is 3a to the 5th minus 2a cubed minus 8a equals 0. And so I have a common factor of a, so 3a to the 4th minus 2a squared minus 8. And then we're going to try to factor this, 3a squared and a squared. I needed to multiply to 8 and add to 2, so I'm thinking I'm going to put the 4 here and the 2 here. So that gives me 6a squared and 4a squared, which if I want it to be negative, then negative 6. So the 2 is negative and the 4 is positive. And then a squared minus 2 can't be factored more, and neither can a 3a squared plus 4. So it's factored completely. So I have a equals 0. I have 3a squared plus 4 equals 0. And I have a squared minus 2 equals 0. And I can solve these. 3a squared equals negative 4. And divide by 3. So a squared equals negative 4 thirds. And now this means I have imaginary roots. And what do we do about those? So I get a equals plus or minus the square root of negative 4 thirds, which solving it is part of this assignment. So it's 2i over the square root of 3. And then we rationalize by multiplying by square root 3 over square root 3. So we get plus or minus 2i square root 3 over 3. Which is totally imaginary. I don't know what we're going to do about that. We'll talk about that in a second. Plus 2. And then, so a squared minus 2 equals 0. A squared equals 2. A is plus or minus the square root of 2. And that's approximately plus or minus 1.4. So we're going to put the real ones on the graph. And then there's a loop somewhere else in that graph, and we'll maybe look at that in Desmos. I challenge you to plug this equation into Desmos and see what it looks like. So we have a 0 at 0, 0, and then we have one at 1.4 and negative 1.4. And so let's look at our end behavior. It's odd. And it's positive. We look at our highest exponent and we look at the coefficient at the front. And so odd positive again looks like this. And I have no double roots, so it's just going to go through those 3. We're not quite sure where it's going to have an extra bump because of the zeros that are imaginary. So let's see about going to Desmos. Okay, so we can type this into Desmos here, and let's see what happens. 3x to the 5th. Oops, that didn't work. To the 5th. What's my problem? Minus 2x squared, cubed, cubed, minus 8x. And you see it looks just like what I drew. So it doesn't have any extra like loop-de-loops in there because of the imaginary. And so we'll just draw it, you know, with the zeros that we know about. Last example, example 4 is 8x cubed equals 1. And so we have 8x cubed minus 1 equals 0. And this is a difference of cubes, which is a cubed minus b cubed equals a minus b, a squared minus, or plus ab plus b squared. This is always the same sign, the opposite sign, and then the positive. Same, opposite sign, positive sign. And the rest is all the same for both the sum and the difference. And in this case, my a is 2x, sorry, not a, 2x cubed minus 1 cubed. So that's 2x minus 1 times 2x squared plus 2x times 1, right, a times b, plus 1 squared. So that's 2x minus 1 times 4x squared plus 2x plus 1. And so I'm solving. 2x minus 1 equals 0. So x is 1/2, add 1, divide by 2. And then to get the zeros here, we have to either complete the square or use quadratic formula. And I'm going to use quadratic formula because this does not factor more. And people want to factor it, but there isn't any way to factor this. So I get negative 2 plus or minus the square root of 2 squared minus 4 times 4 times 1, which is 2 times 4, 2 times a. Negative 2 plus or minus 4 minus 16 over 8, which is negative 2 plus or minus the square root of negative 12 over 8. And so negative 2 plus or minus 2i squared 3 over 8. Divide everything by 2, so negative 1 plus or minus I squared 3 over 4. Those are my imaginary roots. And so because there's only one, right, this is odd positive, it has this inflection point. And it's not really something you have to worry too much about for accurate graphing, but we'll show it in Desmos as well. I'm trying to figure out what I'm doing here. So I have a x-intercept at 0, and I know that my y-intercept's at negative 1. So I'm going to come up, and I'm going to go through that at the intercept. And let's look at Desmos, how that shows up. 8x cubed minus 1. And you can see that inflection point happens at the y-intercept because this is a difference of cubes.